Okay. So today we are going to start by solving this example, and then we will talk about aerodynamic center for just a little bit, and then move on to the viscosity drag calculations. Okay. So I'm going to give you a couple of minutes, like 10, 15 minutes to work on this, and then we'll go over it together. I haven't solved this myself, so I don't have the final answers, final numbers, so someone has to follow me and like do the calculations for me, right? Give me the final number. So this is your airfoil. This is the equation of the camber line. So this is how your camber looks like. Zx. We have x by c, 0 to c, from 0 to 0.5. So something like this, right? 2.5. And at 0.5, we get 0.25 here. And then 2 minus 2xc. So your 2 minus 1. So your airfoil is a very weird shape. This is the real shape of the airfoil. So in real world, this is not something you're going to see, right? This kind of distribution, right? Keep that in mind, right? I will simplify this problem just to make sure you can solve this in a short amount of time. But in reality, no camber distribution will look like this. So this essentially means that our airfoil is something like this, which is not a very helpful design for an airfoil, right? So just keep that in mind. This is just an equation to make sure that your solution is a simple solution. But yeah, we are looking for the zero lift angle of attack. We are looking for the lift coefficient at 4 degrees. We are looking at the moment coefficient around the quarter core. And we are also looking at the location of the center of pressure divided by C, divided by core length. Right. You have all of the equations for it from the previous lecture. Let me actually write down the equations for you, just in case. So zero lift angle of attack is the -1 over pi, 0 to pi dz dx, 1 minus cosine of theta, or cosine of theta minus cosine of theta minus 1 d theta. Okay, that's the equation for the first one. It doesn't really matter if you're using theta node or theta. You just have to be consistent, right? And I guess for part B, you don't need an equation, but for part C, Cm around the quarter core, you have pi over 4, A2 minus A1. A2 and A1 are your Fourier constant. A of n can be calculated as 2 pi 0 to pi dz dx cosine of n theta not d theta. And you can actually let go of this part. This last part is essentially the same. Oh, you already calculated that. Let's actually do this. And x of center of pressure by c, you can find this as c over 4, 1 plus pi over CL A1 minus A2. I've given you a couple of integrals just to make sure you can quickly take the integrals. You don't have to know this beforehand. You can put them in an equation sheet or whatever. And yeah, some trig relations, trigonometry relations. Like cosine of 2 theta is 2 cosine squared minus 1. Which essentially means that you can get the integral of cosine of 2 theta using this. So what was the first thing you needed to do here?
Transform from x to theta.
dz, yeah, you want to take the derivative of z with respect to x, right? That's the first thing you want to do. And then transform that from the x to theta, right? The transform parameter was also this, just in case you don't have it in your 1/2 cosine theta minus 1. 1 minus 1 minus cosine. I want all of you to start working on this. Just in case you don't know where to start, I want to take the derivative of z with respect to x. I'm going to move c to the other side. When you take the derivative, you're going to get 1 minus 2 x divided by c. X divided by c between 0 and 0.5, and then dz dx is going to be -2. I want to use this conversion, this transformation equation, to transform everything to theta. Yes. It is, yeah, all of this is a square. So in this type of problems, usually we present x over c as a package. Yes. Which one? First one or second one? First one, you want to move c to the other side, so you're going to get x minus x squared divided by c, right? Take the derivative of this is going to be 1. Take the derivative of this is 2x divided by c. Okay? And we can do the conversion or transformation next. X divided by c is 1/2 1 minus cosine of theta. So dz dx is equals to 1 minus 1/2 multiplied by 2 is going to be 1 minus cosine of theta 4. Then you have to convert theta as well. This is going to remain the same because there is no presence of x, right? You want to convert these limits. To do so, just have to put a 0.5 here. Is equal to 1/2 1 minus cosine of theta. 2 multiplied by 1. 1/2 is going to be 1. Maybe you should have chosen a different limit here. Then your theta is pi over 2. Are we clear on what is happening here? Yes? Okay. So the next step is just to plug these in into your equations and find the solutions. That's it. The thing is, you have from 0 to pi, you have 2 different equations. So you want to take the integrals from 0 to pi over 2 first, and then from pi over 2 to pi. Something to keep in mind is that this equation will simplify to plus cosine of theta. Let me write here. So this is equals to negative 1 over pi, integral of 0 to pi over 2 cosine of theta for dz by dx multiplied by cosine of theta minus 1 d theta. That's one integral plus pi over 2 to pi negative 2 for dz dx cosine of theta minus 1 d theta. Is this clear? Okay. And then we have cosine squared minus cosine of theta. The integral of cosine squared is this. And what is the integral of cosine of theta? Sine of theta. So negative 1 over pi. Whatever we have over there, 1/2 sine of theta cosine of theta plus 1/2 theta and minus sine of theta from 0 to pi over 2 plus, what is the solution to this integral? Negative 2 cosine of theta, so negative sine of theta minus 2 theta, right? Or negative 2 multiplied by sine of theta minus theta. From pi over 2 to pi. Is this clear? Yes. It was 0 to pi. It is 0 to pi. But our dzdx's, we have two dzdx's in that range. One goes from 0 to pi over 2, and then pi over 2 to pi. So we had to break that integral into two integrals.
So it'll always be in any problem added up. You add up the boundaries, it'll always be 0 to pi.
That's what must happen. Yeah, that was the idea here. So look at this conversion, right? This x over c changes from 0 to 1, right? Put 0 here, your theta is going to be 0, right? If you put 1 here, your theta is going to be pi. Okay? Yes. Did I make a mistake? I'm not sure. So we are clear up to this point, right? Yes? Okay. X over c is 1/2, 1 minus cosine of theta. So you plug in 1/2, 1 minus cosine of theta. 2 will cancel out with 1/2. 1 minus 1 cosine of theta is plus cosine of theta, right? That's it. So let's plug in the values here. If you plug in 0 in this first one, you're going to get 0. Sine of theta 0, theta 0, sine of theta 0, right? If you plug in pi over 2, cosine of theta is going to be 0. This will be pi over 4. And this will be 1, right? So this whole thing, the first thing will be pi over 4 minus 1, okay? Multiplied by negative 1 over pi. And this one, you want to plug in pi over 2 and pi. If you plug in pi and pi, you're going to get 1 minus pi, right? 0 minus pi. So let's do negative 2 pi or plus minus. If you plug in pi over 2, this is going to become 1 minus pi over 2. So negative 2 plus pi, which means that we are going to end up with 3 pi minus 2. Is this correct? I don't know if any one of you have gone that far. So pi over 4, we just have to add them up. This is 12 pi over 4, 13 pi over 4, minus 3. Divided by pi, your alpha, your zeroth angle of attack is going to be negative 13 pi over 4, 13 over 4 plus 3 over pi. That will be the answer to the first part of the problem. Yes.
Where did the 1/2 theta come from?
That's
I
from here.
I didn't see the plus part.
Yeah.
Okay.
So make sure to include this in your equation sheet. Yes.
The second derivative being 3 pi plus 2 instead of minus 2.
Can you say that again?
The second derivative on the very last line on the left side, wouldn't it be 3 pi plus 2 instead of 3 pi minus 2?
3 pi plus 2. 3 pi. No, that's negative 2. Oh, yeah, you're right. I'm sorry. It already has a negative sign. I mean, I probably have made other mistakes as well. So this is going to be 1 over pi then, right? Or is it? That's, yeah, 1 over pi. Negative 1 over pi. Don't rely on the final results here, as long as you understand what's the solution procedure. So this is for the zero lift angle of attack. The next part, we want to find lift coefficient at alpha equals to 4 degrees. How can we find this? How can we find this part? Lift coefficient at 0 degrees. Yes. So you have to go. You're on the correct path, right? 2 pi alpha. That's for CL for the symmetric airfoil, right? We don't need to calculate that equation because we are assuming that CL versus alpha is changing linearly, right? And we have CL here. We have alpha here. What's CL at this point? 0, right? That's the idea. 0 lift angle of attack. So CL is 0. And we have just calculated alpha. We want to find, we have alpha 4. And we know this slope is 2 pi, right? That's what we already know. So how can we, based on this information, how can we find this value CL? It is not that common. It's a little less complicated. How can we find the slope of a line? This is something I mentioned in the previous lecture as well, right? Delta CL is a linear thing, right? Delta alpha, right? Equals to 2 pi. That's the idea, right? Delta CL, that's CL at this point, minus 0, CL at this point, divided by alpha at this point, 4, minus that value, whatever that is. I'm just going to call it alpha 0 lift, equals to 2 pi. So we have alpha 0 lift. We have 2 pi. We know what 2 pi is. We have 4. Then we can find CL. Is this clear? Okay. What about the third part of the equation? For the third part, we want to find the moment coefficient at at the quarter core, around the quarter core. Okay. So this is the equation we are looking at. Well, we just have to find the values of A1 and A2. A1 is going to be, we have the function for A2. A1 is going to be 2 pi, integral of 0 to pi, dz dx. N is 1, so cosine of theta naught, d theta naught, right? Which you can plug in whatever value you have. 0 to pi over 2, dz dx was cosine of theta, right? Multiplied by cosine of theta. So cosine of theta squared, for which we have the solution, the integral 2, plus integral of pi over 2, 2 pi. What's it, negative 2? Negative 2, dz dx is negative 2, cosine of theta, d theta. Can we take that integral? One of them is the integral of -2 cosine of theta, and one of them is the integral of cosine squared, right? Plug in the values, you can find A1, right? Is this clear? How about A2? How can we find A2? A2 is 2 over pi, 0 to pi. Again, dz dx cosine of 2 theta, because n equals to 2, d theta. You have 2 over pi, integral of 0 to 2 pi over 2, cosine of theta, cosine of 2 theta. D theta plus the integral of pi over 2, 2 pi, -2 cosine of 2 theta, d theta. How do we take the yes? These are the, if you go back, we actually had to, for the cambered airfoil, we mentioned that we have to take the Fourier, to use the Fourier method to take this integral, Fourier integral, right? You don't need to know that method. You just have to know the final results. And these are going to be constant in the series for that Fourier method, right? So as for their physical meaning, we have to go back to the Fourier integral to be able to explain those. So just take them as constants here that you need to calculate. And A1 means that n is 1. A2 means that n is 2. Okay? Can we take this integral? What is the idea for taking this integral? Cosine of theta multiplied by cosine of 2 theta.
Isn't there some trig relation with cosine of 2 theta? Oh, wait. Yeah, there it is.
So you can plug that in, right? Cosine of theta multiplied by 2 cosine squared minus 1, which means that you're going to end up with the integral of 2 cosine third of theta minus cosine of theta, right? And we have the solution to the integral of cosine third of theta. So just plug that solution to the integral in here. Plug the numbers, you have A1 and A2. When you have A1 and A2, then these will become pretty simple, right? Just plug in the numbers, you'll get the values. Yes?
When we solve for CL, did we add 13 over 4 minus and 1 over pi to the 4, or did we subtract?
I'm not sure what you mean, but if you go back to the
Equation plus,
okay,
plus
that's
the integral from 0 to pi forever, right? Or do we not even use a different method?
to calculate the CL.
Yeah.
You don't need to take the integral to calculate the CL.
In the notes, it says CL is equal to 2 pi alpha plus 1 over pi integral from 0 to pi dz cosine theta minus.
That's correct.
theta.
That's correct.
So we've already solved for 1 over pi integral 0 to pi dz cosine theta minus 1 theta. Then we can just take the answer from part A.
That's essentially what we did, right?
Yeah. So did you, like just the signs of it, did you subtract the 13 over 4 minus 1 over pi to the 4 or not?
Subtract it from what?
From the 4 at the beginning of that.
It has to be a subtraction, right? Okay. Is there any questions? Are we all clear on how to solve these type of problems, right? So as soon as you can get yourself to this final integrals, which shouldn't take that long, you can just plug in the solution. You don't need to take an integral. You just plug in the solutions, put in the numbers, and get a final value for it. Okay? Does this make sense? Is there any confusion whatsoever anywhere? No? Yes.
Are the formulas for A1 and A2, do they come out to be the exact same?
Can you repeat your question?
Do the formulas for A1 and A2 come out to be the exact same?
No. So this one is the integral of 0 to pi dz dx cosine of 2 theta, because n is 2, right? But this one, A1, since n is 1, is the integral of 0 to pi of dz dx cosine of theta. And that means actually there is a sea of difference between them, between the two integrals. Okay? Just have to make sure that you are careful here. Okay? So if there's no other questions, let's move on. And so in the earlier parts of 20th century, in the earlier days of flight, they had to use this analysis. They had to take these integrals, all of these things, to find the lift coefficient, to find the moments, to find the center of pressure, like location of center of pressure. There were no computers. There were no other methodology that would help them, right? And eventually, they were able to design planes that could fight in the world wars, right? All of the wars, not just World War. Okay. If there's no questions, and again, this will definitely be a question on an exam. I guess with this type of dzdx, so you can just plug in the numbers and find the integrals, right? Not the real lengthy ones. And I probably am going to ask you if the type of dzdx that I'm going to give you, if that can represent a real airfoil, right? We talked about this, that they have to actually meet at the same point, the two sides. But for this specific problem, they didn't meet at the same point. So this wasn't really presenting a real airfoil. Like,
That's because they met the same x but not the same y.
Yes.
Will you show us a graph of the x and y, or will we have to find the y?
Yeah, that's the z. You're finding a z, right? And that we have the z versus x, right? By just plug in the value for x at that limit, and you find z, right? You have two equations that have to meet at the same point, like 0.5, like here, and then you can find the z. Okay, so let's talk about the viscous flow a little bit. I'm talking about the airfoil drag calculations. So far, we have already discussed the lift calculations. We haven't really touched on the viscous flow calculations and airfoil drags general. But we are familiar, hopefully by this point, we are all familiar with the D'Alembert paradox. Who can tell me what the D'Alembert paradox was?
Drag is 0, but there has to be a drag in order for it to be 0.
Exactly. So if you neglect viscosity, what you're going to get in some cases is zero drag, which is an unphysical conclusion, unphysical result, right? In those cases, you have to have drag. That's essentially, this was first observed by this guy, D'Alembert, in the late 18th century. It's a French mathematician, right? He was a French mathematician. That's why the paradox itself is called the D'Alembert paradox. So in order to have a better understanding of the drag, we need to include the effects of viscosity, okay? Before talking about the effects of viscosity, let's talk about the types of drag you are going to see in an inviscid incompressible flow. So for a Mach number smaller than 0.3. What are the types of drag we are going to see? We talked about if you're including the effects of friction, we are going to have shear stress on the walls, right? That was the idea, which is going to result in the friction drag. Okay? But there is another type of drag that is present here, especially when you have flow separation. I think we talked a little bit about flow separation, right? Which means that you are going to have an adverse pressure gradient. And the drag due to this adverse pressure gradient is called the drag by pressure. Some people call it pressure drag or the form drag. Okay. Two main types of drag. In this lecture, we are mainly focused on the friction drag, how to calculate the friction drag, right? And the type of analysis we need to do to find the friction drag. Okay. So a question I have for you is this. What will happen to the flow on the airfoil when you include the effects of viscosity? Or what is happening to the flow on the airfoil in reality, right? In the real case, when you are not neglecting viscosity. Boundary layer formation, right? This is also something that you had in your exam. The idea is the first layer, if we have no slip conditions, which means no layer of fluid can slip on the wall, the first layer will lose all of its momentum to the wall, which means that the velocity here is going to be 0, right? And there is a momentum deficit here. And then this momentum deficit will decrease and decrease and decrease, which means that your flow velocity, fluid velocity is going to increase and increase and increase until it reaches the free stream velocity, u infinity. This region in which we have a velocity gradient from 0 to u infinity, usually the limit is 99% of u infinity, is called the boundary layer. And its thickness is called delta. Very important parameter. So when the velocity is changing from 0 to u infinity. So when you include the effects of viscosity, you are going to see the formation of boundary layers, right? And we have to analyze the boundary layers here to be able to calculate the friction drag. So the point of this lecture is not to prove or derive the equations for this. So I'm just going to give you the equations for boundary layers. If your flow is laminar, your boundary layer thickness, this thickness, you can calculate it as 5 divided by a square root of Reynolds number. That's RE of x.
What is that first term on the top?
5. 5.0.
It's supposed to be times x or no?
Times x. Yes, I'm sorry. Forgot the equation. What is the Reynolds number? Who remembers what Reynolds number is? From your foot, yes.
It's the ratio of space and inertia flows. I forget which one's on top.
Inertia and viscous forces, right? Exactly. Reynolds number on a flat plate is a dimensionless parameter that can be calculated by your density, free stream density, free stream velocity. Let's call it U infinity. The location on the plate, or in this case, airfoil, divided by free stream viscosity. This parameter is called a local or the local Reynolds number. So let's say we are moving on a flat plate, center of coordinate system from here. This is how you calculate Reynolds number. What does this mean for Reynolds number? Reynolds number is a function of x. It means that Reynolds number is going to increase from 0 here. This local Reynolds number is going to increase from 0 to a finite value, right? Whatever the length of this plate is. Your maximum is going to be rho u infinity L divided by mu infinity, right? That's the Reynolds number of the plate. Is this clear? So as you move on your plates, this value is increasing, okay? Which means that your thickness is going to change as well, right? I mean, your thickness is also a function of x. So as you move on, as you move from 0 to L, your body layer is going to increase like this. So this is how we calculate the thickness of the body layer if you are in the laminar region. But the friction coefficient, which is the main target for us, can be calculated using 1.328 divided by a square root of Re Reynolds number. That's Reynolds number for the plate, Re of L, or Re of C, Reynolds number of C. Okay, so two equations, very simple. You can find the thickness as well as the friction coefficient of the plate, right? Is there any questions here? So let's say we are within the laminar region and we want to find the viscous drag. What should we do? Let's say you have already calculated the friction coefficient, which means that you have already found the Reynolds number. I plugged it in here, and you want to calculate the viscous drag. What should we do? How can we use the friction coefficient to calculate the viscous drag? So I think what Muhammad is pointing to is the definition of force coefficients, right? How did we define the force coefficients? It was your force coefficient, in this case, friction coefficient, is equals to that specific force, which here is the friction drag, divided by Q infinity, multiplied by your area, but we are dealing with a two-dimensional case, so that's only the chord length, right? We have the Q infinity, 1/2 rho v infinity squared. We have the C, we can find the friction drag. Okay? So pretty simple. In a laminar region, you calculate the Reynolds number of the plate. Then you plug it into this equation. Then you find the friction drag. Yes. It does depend on the surface roughness, right? There is no term here because we are making the simplest calculation you can make, right? But in general, you are moving in the correct direction, right? To make this equation more inclusive, if you will, you have to bring in the surface roughness as well. But we are dealing with a flat plate here, right? So we are assuming there is no roughness, okay? And that's the starting point, right? Okay. What do you think should happen when you're dealing with surface roughness? When you have a rougher surface, what do you think should happen to the friction coefficient? It should go on. Okay, yeah. So, if there's another question, let's move on a bit. What will happen to our flow when your Reynolds number increases? Or to rephrase my question, I can say, what do we use the Reynolds number for? Why is Reynolds number an important, or what's the distinction Reynolds number makes in the flow? Yes. Exactly. So we use the Reynolds number to determine whether the flow is laminar or turbulent, right? So what will happen to our calculation here if Reynolds number is high enough that we can get turbulent flow? Can we use these formulas? Obviously, no, because these formulas are derived for laminar flow, which means that we have to have another set of formulas for turbulent flow. Okay. The body layer thickness in a turbulent flow can be calculated by .37 RE of x, RE of x to the power 1/5, and the friction coefficient can be calculated by 0.074 REC to the power 1/5. Let me ask you a question. For those of you who have had heat transfer in our university, have you seen these equations before in your heat transfer? Yes, right? Hopefully, we are all of us have said yes to this question. But if not, we have the equation here. So this is how we calculate the friction coefficient. That's the average friction coefficient over the plate. Okay. Well, one thing that is worth noting here is that our Reynolds number increases as we move on the plate, right? Not only it depends on U infinity, rho infinity, so we can have, if you have high enough U infinity, you can actually have a turbulent flow, turbulent body layer from the get-go, right? That's the idea, right? Not really for the body layer, but that's the idea. We'll talk about it. But let's say your U infinity is small, but your plate is long enough, right? You will start with a laminar body layer, but at some point you will transition to a turbulent body layer because your Reynolds number is going to become high enough, right? So there will be a transition point. Who remembers what was the Reynolds number? We call it a critical Reynolds number for the transition from laminar to turbulent on a flat plate. 5 multiplied by 10 to the power 5, right? That's the value we usually use. But in reality, the transition is a region, right? Not just one line, right? So we start the transition from 10 to the power 5. It usually ends at around 10 to the power 2, 10 to the power 6, somewhere around there, right? So, but for the purpose of this course, we are going to assume that the transition happens at one point. We're going to have laminar, turbulent, laminar, turbulent. Body layer thickness in the turbulent flow is a little bigger, is a little higher. But that's not part of the discussion of the class, as long as you know this. Okay. So we have a transition happening, but the equations we have only applies to the case where we either have a complete laminar flow, right, or a complete turbulent flow. from the beginning. And in order to have a complete turbulent body layer, you actually have to trip that's what we call tripping your flow to turbulence. Right? Have some kind of a geometry like this, which means that you are putting a vortex generator here. You are intentionally transforming your flow to the turbulent flow, which is actually a useful concept in a lot of different cases, and a harmful thing in a lot of other different cases, right? So the equations we have only works for these two. The equations do not really work for the case when we have transition, right? So what should we do? How can we use these two groups of equations, or these two equations for friction coefficient, and calculate the friction drag for a case where the transition from laminar to turbulence happens? And I want your opinion on this. What should we do when the transition happens? Are we clear what the problem is first? The problem here is that these equations capture only laminar or only turbulent. But in most cases, we start from laminar, then transition to turbulent, right? My question is, how can I use these two equations for friction coefficient and calculate the friction drag for a case in which transition happens? It doesn't start as turbulent, for example, right? Or doesn't end as a laminar flow. Yes.
You have like 1 multiplied by x and 1 multiplied by 1 minus x, or something like that?
1 multiplied by x, 1 multiplied by 1 minus. What is x here? Which position? What is the significance of that specific x that you are multiplying with? Or is it just a random x?
Like assuming that it starts at like 0 where there's no drag, and it goes from fully 1 to like fully laminar to fully turbulent. At position 0, the one that's 1 minus x would have like nothing. And then the one that was x would have everything. And then at the other side it would have all of the other ones. And like add them both into like the same equation.
But based on what you're saying, that you essentially will have some contribution from the turbulent equation here when you have full laminar. So that doesn't really apply, right? Because this is fully laminar. There is no turbulence here.
Okay, so we're not even worried about that?
We have, yeah.
I thought you said that they were both.
Not. They are both on the same plate, not on the same location. There's a transition happening, right? Let me maybe ask you a simpler question. Based on these two equations, how can we calculate the friction drag on these plates? Like we have two equations for laminar and turbulent flow. Yes.
We just split it into like a piecewise function like we did before and just add them together. So knowing the transition point from x equals 0 to say 0.6 or whatever, it's delta is equal to this, but then after that it's equal to that.
Okay, so let me see if I understand you correctly. What John is telling us is that we can find, the first thing we need to do is to find this critical Reynolds number, right? Critical length, which we can very easily find based on this Reynolds number, right? We have the equation for Reynolds number. Just have to plug in 5 times 10 to the power 5 here. We have the rho infinity, u infinity, mu infinity. We find the critical length at which the transition happens, right? From laminar to turbulence, right? Okay. And then you here, right? You plug in L is equals to x critical, right? And here, for the turbulent part, you plug in this length, right? Is that what you're saying?
Yep.
Are we all clear what John is telling us to do? Yes. Okay. That's a good start, but that's the wrong answer. Why is that the case? right? The reason is the first part, for the laminar part, you're correct, right? You can just plug in the values. But this equation gives us a friction coefficient where the body layer starts with 0 thickness. So if what you're telling us, if we do what you're telling us to do, we're essentially making the assumption that we have a laminar body layer until a transition point, then the thickness goes to 0, and we start back with a turbulent body layer, right? So this solution doesn't apply because we are removing all of this part, right, of the body layer. Add the what?
So you just add the endpoint of that laminar flow.
Add the endpoint to what?
Whatever function the turbulent for that piecewise function.
But how, so you're telling me that we have to add this part to the calculation, right?
Yeah, you just add.
But how can you find the friction coefficient, the contribution of this part of the body layer to the friction coefficient? That's the main problem.
What is the y axis on that?
That's just y. This is thickness, right? Y. There's flow coming in. We have a body layer. This is the thickness of your body layer.
Oh, so delta is the.
Delta is the thickness, right? This is delta.
This is delta. Okay. Yeah, so just add the previous delta.
Add the previous delta.
Every single calculation in that next part. And then you can just use the curve plus delta.
So you're telling me that I have to use this friction coefficient plus the laminar. This part is laminar contribution, right? Is that what you're saying?
Yeah, plus that one spot at the end.
Your friction coefficient equation is not a function of delta. So what do you see? This is 1.328 divided by the square root of Reynolds number.
Delta would be a constant there.
Pardon me?
Delta would be a constant there. It's just delta. I can't really see what that point says. I think that's XCR, X critical.
That's correct.
Yeah, it would just be delta critical then. Delta at X critical.
But you don't know how to calculate the friction coefficient at that specific point. So you can't just calculate it and add it. Does this make sense? Okay. Do you have any other opinions? Yes. So you are telling me that we can just assume that the contribution of laminar part of the flow is small? Is that what you're telling me? I'm not sure I'm following. I think you are talking about the fact that within the turbulent body layer we have different regions, right? Right? Is that what you're saying? But that's so I'm not sure I'm following what you're saying. Okay. Is there any other opinions? No. Yes.
So that be like the convergence point would be like the specific Reynolds number where you actually use transition from like laminar to turbulent, and you can assume that you use the laminar even before that.
Okay, your conclusion was not the right conclusion, but your starting point was a very good starting point. What if we calculated the laminar or the turbulent flow, because the transition only happens in the turbulent? What if we calculated the drag force? Assume that the turbulent flow starts from the beginning, right? And we calculated drag force for that part. You can definitely do that, right? So calculate the drag force. I'm going to assume that, let's call it D turbulent and L for the whole plate. Okay, and we can only do it for the drag force. This is what you were saying. That was the starting point, right? And then the next thing we can do is to calculate, to use the turbulent friction coefficient equation. Where is the one? To use the turbulent friction coefficient equation, right? To calculate the turbulent drag force for the laminar region, right? Right? So we want to calculate the drag force for all of the plates. Then we calculate the drag force for the laminar region, right? Using the turbulent equation, right? And then if we subtract these two forces, all of the plates, ETL and laminar, we are gonna, the only thing that remains is the contribution of the drag force in the turbulent region. That's the only thing that remains, right? Does this make sense? Okay. The turbulent and turbulent, let's call it. Does this make sense at all? So essentially, you assume that all of the plate is turbulent, do the calculation, then you remove the part in which the flow is really laminar, right? You're gonna only have the turbulent drag where the flow is turbulent, and then for the laminar region, you just calculate use the CF, this equation, the laminar equation, make the calculations, find the drag force, add this to your laminar calculation, the laminar and laminar, and that will give you the total friction drag, dF. Yes?
What is the problem with that? Is that the turbulence doesn't start at zero? Like that would make sense if turbulence started at zero and all of the laminar flow was inside of the turbulent flow. But like it looks like turbulent flow begins at like, I don't know. Like,
X critical, yeah. That's why we are removing all of the laminar parts of this calculation, right?
it looks like if you were to continue the graph, it would get the x-intercept at like 1/2 x or whatever.
That's what. Let's actually, if it is not a question from everyone else in the class, let's talk about it after the class, okay? Okay. So, is there any questions here? Is this clear? This is how you calculate the viscous friction. Let's solve an example. One thing that I forgot to mention, that I need to mention, is how we calculate the location of the aerodynamic center. The location of aerodynamic center is calculated using this formula. I'm just going to give you the formula, and hopefully you will remember this. I forget the formula. I always forget this for whatever reason. Aerodynamic center is negative m0 divided by a0 plus 0.25. And m0 is dcm, d alpha, a0 is dcl, d alpha. That's dcm around the quarter. Okay. That's the location of aerodynamic center. What was the aerodynamic center? Who remembers what the aerodynamic center was?
Where the net force is zero, not the moment?
No. Aerodynamic center was a point at which moment doesn't change with respect to angle of attack. So changes of angle of attack doesn't change the moment, net moment, okay? Moment is not zero, but it doesn't change, right? Okay. And let's solve a viscous drag example. That's the lift slope. Yeah. dCl over d alpha, not dx, d alpha. Cl alpha. This is dCl d alpha. Okay? What is dCl d alpha for a thin airfoil? 2 pi. That's it. This is something we have calculated. Okay. Let's see if we have enough time. I don't know if we have enough time for this example, though. So we have this is also a very important calculation that will probably show up in an exam. So you want to make sure that you are clear. We have this flat plate. Flow coming in is V infinity with V infinity. And the critical Reynolds number is 5. That's critical Reynolds number. 5, 10 to the power 5. Let me give you the other dimensions. The Reynolds number at the end is given to us to be 3.1 times 10 to the negative 6. And we want to calculate the net skin friction drag based on this information. Yeah, these are the only information we have. How can we do that? 4.7. Let's see if there is only. I'm going to give you 2 minutes to think about it. Just 2 minutes. And yeah, that's all of the information we have. We have the Reynolds number at the end location, at the end point. And we want to calculate the total skin friction drag coefficient, or skin friction coefficient. The first thing you want to find is the transition point, right? How can we find the transition point here? Can we find the transition point as a ratio like this? Let's call the transition point x1. Can we find the x1 divided by c? Can we find this? We have one no. Do we have any yeses?
Yes.
Okay. Can you elaborate on that? No. Okay. That's all right. So, what can you say about this operation? R a critical Reynolds number divided by R of C. What can we calculate from this? This is rho V x critical divided by mu divided by rho V C divided by mu. Yes. That's it, right? So John was correct. We have the two Reynolds numbers. We can find x critical, x1, let's call it x critical. We are not given the coordinate. Do we need to have the coordinate? We'll see. Okay, so what is this value? 5, 10 to the power 5 divided by 3.1, 10 to the power 6. Five divided by 31. Can you calculate this for me? Let's see if we have it here. 1.6. We actually have it here. 0.16, not 0.16. Okay. And we want to find the net skin friction coefficient. Let's see what we can do. Your drag force, total drag, friction drag is equals to the laminar drag, right, minus the turbulent drag for the whole plate, right, minus the turbulent drag for the turbulent region. So I'm just going to call it turbulent drag of x critical and turbulent drag of the, or it's actually the other way around. That was the idea, right? This is something we just discussed, right? Is this clear? Okay. How can we calculate the total drag based on the definition of force coefficient? What was the equation there? CF multiplied by Q infinity multiplied by your chord length or x critical, depending on the length, right? Okay. So this dF is your net CF, right? Net friction coefficient. This is something that we want to find. So CF, I'm going to call it CF net, Q infinity, and this is true for the whole plate, multiplied by C, right? Is this clear? This is equal to the laminar portion of it. How can we find the laminar portion of the friction coefficient, or the friction coefficient in the laminar boring layer? How can we find that? Same equation, except for the laminar part of the flow. Q infinity x critical, right? Yes? Okay. Plus this part. Drag force, assuming that all of the plate is turbulent. So CF, assuming all of the plate is turbulent, multiplied by Q infinity, multiplied by the length of the all of the plate, which is C, minus drag force, turbulent drag force of the laminar region, right? We want to take that out. So CF, turbulent and laminar, whatever, Q infinity, x critical. Is this clear? Is this clear? Is this clear? Yes. No. Where's the question? Okay, let's just start from the beginning. Not the beginning, but let's go back a little bit. Total drag force on this flat, total friction drag on this plate is equals to the friction drag of the laminar region plus the friction drag of the turbulent region, right? Turbulent, right? So how did we calculate the turbulent drag, the friction drag of the turbulent region? We calculate the friction drag of the whole plate using the turbulent formula, and then we subtracted the turbulent drag of the laminar region, which we have calculated using the turbulent formula. Okay, is this clear now? Okay, turbulent and laminar. So this is the turbulent drag of the laminar region, but we have used the turbulent equation to calculate it, which means that this is the unphysical part we are taking out. Yes. That's the turbulent drag of the whole plate. Okay. And we are already out of time, so if you want to leave, you are welcome to do so. I mean, you could have left anytime. But how did we calculate the drag coefficient using the force coefficient definition? Q infinity CF multiplied by your C. This is equals to Q infinity CF laminar multiplied by X critical plus Q infinity CF turbulent of the whole plate C minus Q infinity CF turbulent of the laminar region X critical. Are we clear on what happened here? This part, the laminar part, only is true from 0 to X critical, right? Okay. So the X here in the fourth, this was the definition of friction, the coefficient, right? D Q infinity C. This was the definition. But here, for the laminar part, this C is actually X critical because this only applies to 0 to X critical, right? So the length of the plate is X critical, right, for the laminar region. Turbulent region, the length of the plate, the first part of the turbulent region, which assumes that all of the plate is turbulent, the length is C. The second part that we want to take out, the unphysical part, it also applies to the X critical, right? So we can remove Q infinity from this equation, right? And then I'm going to move C to the other side. So CF is CF and laminar, X critical divided by C plus CF and turbulent. This one is a CF, that turbulent CF that assumes all of the plate is turbulent, multiplied by C divided by C is 1, minus CF and turbulent for the laminar region, X critical divided by C. We already have the X criticals divided by C, that's 0.16. The only thing we need to calculate are the CF. What was the equation for the laminar CF? I don't remember. That's 1.1327, something like that, right? I don't remember exactly, but the square root of Reynolds number of the length, which is going to be the critical Reynolds number. So you plug that in, find the CF, right? And we also had the equation for the laminar, for the turbulent, RE to the power 1/5. Plug this in, plug the Reynolds number in, calculate the CF. And eventually, you should be able to find the net CF. Yes? Is this clear? Okay. So let's stop here. And
Do you want that work we did beginning of class or no?